Hello, my name is John Noguera. I am the Chief Technology Officer at SigmaXL. Welcome to our webinar, What's New in SigmaXL version 9.1. This is part 3 of the 3-part series, Multiple Response Optimization. Our website is sigmaxl.com, and feel free to connect with me on LinkedIn at this address. PowerPoint and data sets that are used. There are some new data sets that are not in the workbook, but they will be available for download as well as the PowerPoint. So with that, we'll start. So our agenda, we will do an introduction to multiple response optimization and look at the multiple response optimization dialog. We'll talk about the desirability function. We'll look at a very simple example to start, which is the robust cake example. This is something we've used before in other examples, other case studies, and is a nice introduction to robust design. Example 2 is the washing treatment of mullet fish. And this is a new example. That's something that we have not used before. And so that'll be an interesting one where in food sciences, they have a washing treatment and things like whiteness and springiness are parameters of interest. And it's a multiple response optimization problem. Example 3, time permitting. I'll talk about that. Chemical process yield from Montgomery's textbook on design of experiments, and then questions and references. So to begin, multiple response optimization optimizes multiple responses with different objectives and importance. So to provide a unique optimal solution, the problem is formulated as a single objective optimization problem by maximizing the Derringer and Suich desirability function. Okay, so Derringer and Suich, the reference is from Journal of Quality Technology. So it's an important paper that gives the methodology and the formulas in what we're doing here. So this is the basis on which SigmaXL uses the desirability function, comes from this paper. And for each output, a desirability is assigned within a range of 0, which is unacceptable, and unity, 1, which is ideal. The individual desirabilities are combined using a geometric mean to create a composite desirability. And so you end up with a single response that you will then maximize, and in so doing, you're taking care of all of the individuals. Some individual responses might be to maximize, some might be to minimize, some might be to hit a target, some might have different importance, and you can control all those individually, and then you come up with this one composite desirability. It's a geometric mean because what happens with geometric is that if you have a 0, the composite is 0. So there's basically a huge penalty if any of the individual responses are unable to satisfy the minimum requirement, minimum specification, then it's a no-go. All right, so the composite becomes a 0. So that's really the main advantage of the geometric mean. This is our dialogue, and we'll be looking at this in detail. But basically, you use the multiple regression, the new advanced multiple regression, to create your models. And then you select your responses, and you specify your goal as either maximize, minimize, or target. You specify a lower bound, a target, an upper bound, weight and importance. The default are 1, and we'll talk about these in just a moment. You specify what method you want to use for optimization, and you have 2 choices: multi-start Nelder-Mead and Medako, mixed integer distributed ant colony optimization, which we talked about in the second webinar for best subsets. Here we're using it for multiple response optimization. Another option that we'll talk about is this use optimize options. All right, so the menu It's under SigmaXL, Statistical Tools, Advanced Multiple Regression, Multiple Response Optimization. And as I mentioned, you're selecting responses from the available models in the workbook that have been created using Advanced Multiple Regression. This will not work with the older regression tool. You have to use the Advanced Multiple Regression in order to work with the Multiple Response Optimizer. If the goal is target, that's the individual response goal is target, a target value must be specified, and it has to be greater than the lower and less than the upper. If a response goal is to maximize or minimize, target is not used. So this is actually a little bit different than other software tools which use target. We use target only when the response has a goal that is a target. All right. Now, so as I mentioned, lower and upper limits must always be specified. So if you have specification limits, then use specification limits. Or if you have a practical limit for maximization or minimization. So for maximization, a practical upper limit would be a value beyond which an increase in desirability is not beneficial. For minimization, a practical lower limit is a value below which an increase in desirability is not beneficial. Okay, so in a maximization problem, your lower limit could be a lower spec limit and some economic upper number. If it's always bigger is better no matter what, then you just simply plug in a large number. So that's, that's fine. You can, but you do need a value. You have to have both a lower and an upper. Now, the initial values for lower and upper are those that come from the response values. So if you have an experiment, historical data, the Y values, the max and the min, are used as the initial lower and upper values in this dialog. All right, so you can go ahead and use the defaults, but if you want to change that, then you would change that in the dialog. Importance. Importance allows for weighting of the response according to relative importance. So use a value between 0.1 and 10. So the default is 1. So if they're all 1, that means all of the responses are of equal importance. But if you want to place more importance on 1, you could have a 10 and a 1 and a 0.1, for example, if you have kind of like a primary, a secondary, a tertiary response. Then you can use this to guide the calculation so that it places the importance appropriately. The default is 1, and that's in all of the examples that we're going to be using. That's what we will have, is importance score will be the same across the responses. Weight, think of weight as a shape factor. So for weight equals 1, the desirability function increases linearly. For weight less than 1, the function is concave, so low priority on hitting the target or goal. For weight greater than 1, the function is convex, so you have a high priority on hitting the target or goal. And we have a nice graphic here that shows you. So this is for maximize. So basically what happens in the default case is that you have a nice linear increase, all right? In the case where the R, the weight is 0.1, you're going to have this curve. And if you have 10, you will have this curve. So you can see this curve prioritizes the target. This curve diminishes the target. And this is just a nice linear increase. Now, just a note, for those of you familiar with optimization and differentiation, because this is not smooth, it's not differentiable, so we do not use Newton-Raphson techniques. We use Nelder-Mead, which can work with non-smooth surfaces. And then the other, Medako does not require a smooth surface. So we're able to use these non-smooth, linear, or curved responses. And in the minimized case, it's just basically the opposite, where if you have a weight of 10, you have this sharp drop. If you have a weight of 0.1, then you have this gentle drop, and a weight of 1, you have this nice linear decrease. Here's the desirability target. So it just kind of shows you with the weight of 10, you have this really sharp peak. So in other words, you really need to hit that target in order for you to get a desirability of 1. Whereas if you go with 0.1, you can kind of almost anywhere within this window get a decent desirability value. Or if you just go with the linear, which is the default, it's kind of in between those two. So I like this diagram to just help illustrate the selection of weight. We will use just a weight of 1, but it's important for your flexibility or to realize that you have this ability to control both importance and weight. So as I mentioned, the method that we use, the default method is Nelder-Mead simplex. It's derivative free, so it can accommodate a non-smooth desirability response with both continuous and categorical predictors. So it's very flexible. Now, it's also very fast, but the big disadvantage is that it gives a local solution. And in these problems, it's often there are multiple local solutions and one global solution. So the workaround to that is to use multi-start. So you have random starts, and then you run the Nelder-Mead and you find a solution, and then that improves your odds. So if you run it 100 times, 100 starts, then you have a better chance getting a global solution. Okay. Also, if there are a number of equally valid best solutions, the one with the smallest predicted response standard error is chosen. So that's done in the background. It's just that when you're doing 100 or even 1,000, whatever number of tries, amongst those, you may find a number of equally valid solutions. So it's going to actually go through and pick the one that has the smallest predicted standard error. That's due to the model uncertainty, of course. So it just picks that out and we'll pick the minimum. Now, the other option is, this is more for if you have a complex response, or maybe you have a large number of responses. By the way, we can accommodate up to 9. So that's the limit in SigmaXL. But so if you have, say, a large number of responses or a complex, and there are multiple local solutions, then use the Medako. You can try both, of course, and see what you get. It's just that this will take about a minute to solve, whereas the Nelder-Mead is quite a bit faster. All right, so that's the mixed integer distributed ant colony optimization. We also use that in best subsets. Use optimize options, predictor bounds levels. Okay, so in the model, you can constrain continuous predictors to a range, or you can actually constrain it to one value, or you can specify the predictors as integers. If you have, let's say, continuous integer values, like on the catapult, pin 2, pin 3, pin 4, you can then specify integers. Or you may have categorical predictors, customer type 1, customer type 2, customer type 3. You can specify if you want to consider all categorical predictors, or if you want to only consider a specific level, then you can hold to a specific level. Now, because you're actually modifying the individual models, what we do is if there's a conflict in the constraints, the lower bound used in MRO is the maximum of the lower bounds, and the upper bound is the minimum of the upper bounds. So you actually only need to change one of the predictor bounds, and it will automatically pick that up and use that as the constraint. So you don't have to go through and change all of them in every response. Also, if any of the models flag a continuous predictor as an integer, then it is assumed to be an integer continuous for multiple response. Now, the only thing is for categorical levels, if there's an inconsistency across levels, then MRO is going to use all levels. You would have to actually go through each model and specify a particular categorical level. So it's a little bit of inconvenience, But that's actually very rare. Most of the time for MRO problems, we're dealing with continuous predictors. Anyways, coming say from a designed experiment, but I just want to mention that is something that needs to be done if you want to specify a specific categorical level. Most of the times you want to leave that open and just let it solve for the best one. All right, so that's the categorical. Another point is that we do not have an interactive desirability calculator. The report is static, but what you can do is if you want to view desirability results for specific inputs, use the optimize options and then just type in the specific value, lower and upper the same for the predictors. And then when you run MRO, it will use these specific values that it won't do any optimization. It will just produce the results. All right, so that's just a comment on if you want to try out a specific value, then you just change the optimize options. Now the formulas from Derringer and Suich, if you have larger is better. If the response is less than the lower bound, then the desirability is 0. If the response is greater than the upper bound, then the desirability is 1. And here's that linear slope if you use an R value of 1. And so basically you just have that rising slope. And here is the minimum. So on the minimum, if it's less than the lower, desirability is 1. If it is greater than the upper, the desirability is 0. And this gives you your downward slope. And then you have your hitting the target. Basically, you have your positive portion, your negative portion, as we saw on the diagrams. Okay, so that's the desirability function. And then you put it all together with this geometric mean. This is where the importance scores come in. And as I mentioned, the reason for the geometric mean is that if any individual desirability value is 0, the overall or the composite desirability is also 0. So we're ready to look at an example, and the example is the DOE example robust cake. So this is a very, very simple example, and we'll bring that up. So this is from our workbook, and this comes from a video called Designing Industrial Experiments, Box, Biscard, and Fung. It's an oldie but a goldie. And you have 3 factors: flour, butter, and egg. And we're not given the actual settings. We're just given the coded values of -1 to +1. The response is a taste score on a scale of 1 to 7, where 1 is awful and 7 is delicious. The outer array repetitions, that's these replications, have different cooking time and temperature conditions. So it's kind of like a Taguchi experiment where you have different time and temperature conditions that are used, and the goal is you want to maximize the mean taste score and minimize the standard deviation. All right, so that's, again, a pretty straightforward experiment. Oh, by the way, aside from this one example, I'm not really going to spend much time looking at the analysis. The goal of this presentation is to talk about the multiple response optimization. We're not going to be doing any type of model refinement techniques. We're just going to go with, if it's from a published paper, we'll use the models that are given in the paper. And in this case, we have in the workbook, we've already solved it, but let's have a look at the main effects and interaction plots, because that's kind of interesting. So here, let me make this a bit bigger. We see that as flour increases, we have an increase in the taste score. As butter increases, we have an increase in the taste score. And egg increases, we have an increase in the taste score. But what's most telling is this two-way interaction, very strong two-way interaction, which is the butter by egg interaction. The taste score for egg, the response for egg depends on what the butter is. So if the butter is low, we have a good average taste score given egg equals 1. But if the butter is high, then we have a lower taste score. Conversely, if egg is -1 and butter is low, then we have a low average taste score. And here, if egg is low and butter is high, then we have a higher taste score. But the optimum value is here, which is butter equals -1, egg equals +1. This gives you your maximum taste score. So you have this very strong interaction. So that's something we definitely want to include an interaction term in the model. All right. The other thing I want to point out is this is the standard dev. Now for standard deviation, you want smaller is better. So you want maximum flour to give you the minimum standard deviation. All right. So this suggests flour equals 1, egg equals 1, and butter equals -1 is going to be the optimum. So I want to start with that. Let's go back to the design. And now we're going to create 2 models, and we're going to run multiple response optimization. So we'll go to advanced multiple regression, fit multiple regression model. We're going to start with the average, and we're going to use butter and egg. I'm not going to standardize because it's already coded, so there's no need to standardize here. So butter and egg, and then I'll turn off residual plots because, again, we're just going to go straight to MRO. I'm going to add the interaction terms. So now I have butter, egg, and butter by egg as my model. And this gives me a good model, 93%, R-square adjusted, 87.5, so pretty good model. And I can actually, if I want, I can optimize, I can say maximize. And here we go, we see butter low, egg high for this model. Flour was not included in this particular model. Now I'm going to recall SigmaXL dialog, and I'm going to change the response to standard deviation, and I'm going to use flour as my predictor. Just a real simple model. It's a simple linear regression. And there's your flour. It's significant. And the goal here is to minimize. So if I minimize and then I run optimize, that's my setting. So flour high gives me my minimum standard deviation of taste score. Again, very, very simple model. So we already know what MRO is going to do, but I like to start with a simple one before looking at a more complex one. By the way, the R-square is not quite as good, but that's often the case with a standard deviation, that you're not going to get quite as good of a model as you do a mean model. So now I want to run the MRO on this because I've established the 2 models, and I'm going to go advanced multiple regression, multiple response optimization. Response 1 is average, response 2 is standard dev. I'm going to use the defaults, which, as I mentioned, this is the minimum of the Y for average. This is the maximum. And I want to maximize average taste score, and I want to minimize the standard deviation. I'll just go ahead and use the defaults for optimization. And voila, butter low, egg high, flour high gives us our maximum composite desirability of 0.88. No surprise. And you have your predicted response value and your standard error and your confidence interval and your prediction intervals. Okay, so that's the first example. Very straightforward, very basic. And we'll look at one more example, which is the fish washing treatment. So this comes from an actual food sciences study, and the paper is mentioned in the back. This is the actual paper, Effective Washing Treatment on Quality of Minced Mullet Flesh. So it's a real experiment. And it's a 4-response, 3-factor central composite circumscribed response surface design to study the effect of washing treatment on the quality of minced mullet fish flesh. It's because it's 3-factor. The alpha for the axial values in the central composite is 1.682. That's going to become important when we do the analysis. We need to specify that. 3 center points were used. And just a point, there is a typo in the paper, and so we use 49.31 rather than the 29.31. The responses, there are 4 responses. Y1 is springiness, the degree to which a deformed material returns to its undeformed condition after compression test. The goal is to maximize springiness. Y2 is TBA, thiobarbiturate acid. This is a quality measure, and lower is better. So the goal for Y2 TBA is to minimize. Y3 cooking loss is basically 100 times the raw weight minus the cooked weight divided by the raw weight. You want to minimize your cooking loss. And finally, Y4 whiteness is measured on the color difference meter based on a white standard, and you want to maximize the whiteness. So you, again, maximize springiness, minimize TBA, minimize cooking loss, and maximize whiteness. The control X factors, you have washing temperature, you have washing time, and washing ratio. And the ratio is water volume over sample weight. So this experiment is all set up, and we're going to analyze the 4 responses. So I'm going to go through, and we're going to analyze each model. And what we're going to do is, the way the paper did it is that they used a full quadratic model for all 4 responses. You can, of course, go through and do model refinement, but we're not going to do that. So we're just going to keep it real simple. We're going to follow what was done in the paper, and we will use main effects plus 2-way interactions plus quadratic terms for all 4 responses. Okay, so this is our data. So we have wash temperature, wash time, wash ratio, and then Y1 springiness, Y2 TBA, Y3 cooking loss, and Y4 whiteness. So we go SigmaXL, statistical tools, advanced multiple regression, fit multiple regression. We're going to put the 3 X1, X2, X3 as our continuous predictors. Y1 is springiness. Now, I need to tell SigmaXL that this was a central composite design in order to get the coding to match the analysis in the paper. So 1.682 was the alpha for axial. That's the coded value. That's these values here. The coded values are plus or minus 1.682. So you want to check standardized continuous and set that to coded. And then that will take care of, in the regression analysis, the coefficients are all going to match what we get from the paper. And other than that, I'll turn off residual plots. And then we're not going to do anything in advanced. We're just going to go straight ahead, and we're going to build a full quadratic model. So that's main effects plus 2-way interactions plus quadratic terms. Okay, so you have your interactions, x1, x2, x1, x3, x2, x3, x1 squared, x2 squared, x3 squared. That's your quadratic model. And this is our springiness. So if I want, I can maximize my springiness. And that gives me a potential setting. Now the problem is this is optimizing a single response, I can also do contour plots. All right, so again, maximize the springiness. You can kind of see here on the surface plot where you get your maximum springiness. But that's just one response. Now, what I'll do is I'll recall SigmaXL dialog and we'll do TBA. Hit next. Now, because I've reset the response, I need to go back and say I want the two-way interactions plus quadratic. I'll select all. Okay, so this is the model for TBA, and the goal here is to minimize. So I can run that and I can minimize my TBA. So this gives me potential settings. I can look at contour plots. And again, here I can view contour plots. But keep in mind that we have 4 responses that we have to simultaneously satisfy. I want to make a comment on overlay plots. Overlay plots are commonly used. Unfortunately, in Excel, there's really no good way of doing that. You can actually use transparency mode for some of these, but it's not really ideal. So you can look at the contours as a guide, and then we're going to use the desirability function to tell us where that sweet spot is. Okay, so this is response number 2. And now Y3 cooking loss. Again, we'll repeat the analysis. We'll build a quadratic model. And cooking loss, we want to minimize. So we'll change this to minimize. And I can run optimize. And there's my settings for my minimum. And then I can look at contour plots. By the way, the reason I do the minimum before I run the contour plots is so that my hold values are at least close to the sweet spot. So, because you can only look at 2 variables at a time. So this gives you, by using the hold values after optimization, you get more useful contour plots. So this is our cooking loss. And then finally, we have our whiteness. And whiteness we want to maximize. And the whiteness model is not quite as good R-square-wise, but we're going to maximize, run the optimizer. This is our maximum whiteness, and again, we can create contour plots. Okay, so we now have 4 models, and what we want to do is we want to run statistical tools, advanced multiple regression, multiple response optimization. So we want springiness, TBA, cooking loss, and whiteness. Springiness, we want to maximize. TBA, we want to minimize. Cooking loss, we want to minimize. And whiteness, we want to maximize. All right, so on this problem, we are going to use the defaults. So we don't need to change anything in a lower, upper, weight, or importance. We just set the goals and we'll go ahead. So basically what we're saying is that the min and the max of the response are going to be the lower and the upper for the MRO. All right, let's run that. Again, I'll still use the default multi-start and Elder-Mead. And our composite desirability is 0.9, so that's good. These are the settings that are given. So temperature, 30.4, time, 8.7, and wash ratio of 24.3. And if we compare to the results in the paper, basically, we actually do a little bit better. So this is basically a capture of, so the Y1, our Y1 is a little bit better than the one given in the paper. Our Y2 is a little bit lower than what's given in the paper. Our Y3 is a little bit lower than what's given in the paper. By the way, these are reversed, another typo in the paper. And the only variable that is not quite as good, but still pretty close, is Y4. So we have 51.3 versus 51.36. So we did quite well finding that sweet spot that simultaneously optimizes the four responses of springiness, TBA, cooking loss, and whiteness. All right, so that's the second example. I think what I'll do for the third example is let me just show you some of the slides so at least you can see what was done. We don't have time to actually go through and do it. So this is a third example is a chemical process yield, and this is the responses are yield, viscosity, and molecular weight. And it's quite a popular example because it comes out of Douglas Montgomery's textbook, and that's a popular book on designed experiments. And when we go through, this is the actual data, and we do exactly what we did before. We just build the models for each. So we build a quadratic model for yield, and we run the optimizer. This is what we get for yield. We do viscosity. Viscosity has an upper and lower spec limit. So yield, you want it to maximize. Viscosity is a target. So we want to hit a target of 65. And that's the contour plot for viscosity. And then molecular weight, you want to minimize molecular weight. And for molecular weight, here's the contour plot. By the way, so in the Montgomery textbook, they use a mean effects model for molecular weight, a quadratic for the first two, but they use a mean effects model for molecular weight. So that's what was done here. Then you go ahead and you plug it in. So you maximize the yield, you hit the target for viscosity, and you minimize the molecular weight. These lower and upper settings are not the defaults. They are the ones that are used in the book. And at the end, we get a good composite desirability of 0.95, and the predicted response is 78.5, which is actually where you want to be for your maximum yield. It's not the largest possible yield, but it's given the constraint that you want to maintain your viscosity at the target of 65, and you want to minimize your molecular weight. This is a good solution. And then, of course, for all of these, you need to go and you need to do confirmation experiments, validate the results. Keep in mind that one of the things that desirability doesn't do is take into account model uncertainty, nor does it take into account your inability to control your inputs. So in SigmaXL in 9.1, the equations are portable. So if you have DiscoverSim, it's actually very easy to set this up as a DiscoverSim model and then do Monte Carlo simulation. So you can actually include the, let's say, the RMS error of the model, and then you can include the uncertainty on the inputs and then get a more robust response. But that's out of scope for this presentation. But I just wanted to mention that kind of as a bonus is this portable version of the formula. And these are Excel range names, so it's very easy to set it up using Excel range names. And that concludes our presentation. So I will look to see if we have any questions. So hello, Ramon. Thank you for joining with us. And if anybody has any questions, please feel free to type them in. Something I wanted to mention that if you do want to use the optimize options predictor bounds, then you need to check this box, all right? And then any constraints that you put on the predictor bounds, so that's back in the model. If you scroll across under the optimize options, any constraints that you put will be applied in the MRO as well. So these are the constraints for the individual optimization. If you have an integer continuous, you change that 0 to a 1. If we had categorical predictors, you would have combo dropdown. But in order to use it, you must check this use optimize options predictor bounds levels. Well, I'm not seeing any hand waving or questions being typed, so I guess we will call that a wrap. And I do thank you very much for your participation. We currently don't have any webinars scheduled, but we'll post those as they are available. And as I mentioned, in 2 to 3 weeks, this will be available for viewing. And I guess most importantly is any feedback you have on using the new features in 9.1 would be greatly appreciated. We're always looking for voice of the customer to improve. We have some exciting things coming in 9.2, including wizards or guides for hypothesis testing and for graphical tools, and that'll be later in the fall. So we've got some nice things coming along. Okay, well, again, thank you all very much, and I look forward to seeing you in the next webinar whenever we have that scheduled. Thanks and goodbye.